The Bragg's law relates the angle of the XRD peak to the spacing between the lattice planes. Its approach is the simplest way to explain the relation between the X-ray diffraction angle and the crystal structure. In the derivation of the Bragg's law, a crystal is regarded as a stack of reflecting lattice planes of separation T, and each lattice plane is regarded as a semi-transparent mirror. Some of the X-rays are reflected off a plane with an angle of reflection equal to the angle of incident, but the rest are transmitted to be subsequently reflected by succeeding planes. Consider the reflection of two parallel beams of the same wavelength by two adjacent planes. One beam travels from point A to R, is reflected by the upper plane, and then travels from point R to L. The other beam travels from point B to S, is reflected by the lower plane, and then travels from point S to M. From the diagram, we can clearly see that the beam reflected by the lower plane travels an extra path length from F to S and then to G, as compared to the beam reflected by the upper plane. This extra path length is marked by the red lines here. If this extra path length is equal to a whole number of wavelengths of the X-ray used here, the two reflected beams will interfere constructively with each other, and an intense diffraction signal should be detected at the location of L and M. Can we further express this extra path length with some quantities related to the crystal structure? In this magnified diagram, the angle between the incident beam and the lattice planes is theta. Hence, the angle FRS and GRS are both also theta. The extra path length from F to S to G is twice the length of line SG. Then, what is the length of line SG? It is equal to d sine theta, because the length of line RS is d, and the angle RGS is a right angle. When this path length difference is a whole number of X-ray wavelengths, the reflected waves are in phase and interfere constructively. In this case, an intense signal will be detected. Now we have arrived at the Bragg's law, which describes the relation between the Bragg angle theta and the d-spacing of the lattice planes for a constructive interference to occur. 2d sine theta equal n times lambda. Here, d is the d-spacing of the diffracting planes. Theta is the angle of incident, and is also called the Bragg angle. N is an integer and can be 1, 2, 3, etc. For the first order diffraction, n is taken as 1. The Bragg's law links the Bragg angle theta and the d-spacing. We can calculate either of them when the other and the wavelengths of the X-ray are given. This is why the Bragg's law is so important and useful in X-ray diffraction. Before we end this video, it is worth mentioning that treating the layers of atoms as semi-transparent mirrors, as what we did here, is more of a concept rather than a physical reality. What really happens inside the crystal can be better described as interactions between the incident X-ray and the electrons in the atoms. Such interactions generate oscillations and emit radiation. This emitted radiation is actually what we call the reflected beam. This is the end of the video. Thank you for watching.